Okay. All right, then I guess we can start, and it's my pleasure to introduce Leila Smajlovic, who will talk about an extension of the Rohrlich-Jensen formula. The floor is yours, as they say.
Thank you very much, Claire. So now I know how to pronounce Rohrlich. Thank you. So I thought it's different, but that's great. You always learn something. So thank you very much for the invitation to give a talk on this interesting seminar. So I will talk about joint work with Jim Cogdell and Jay Jorgensen. So the title you've already heard. So I will begin with an overview of the talk. So the talk will consist of 4 parts. The first 2 parts are kind of overview and motivation. I will first give an overview of previous results on modular versions of Jensen's formula. Then I will discuss on how to revisit Rohrlich theorem and view it as a kind of an inner product formula. Then I will discuss the main results of this work. And if the time permits, I will present applications and some explicit computations for some special groups we chose. Okay, so let's begin. So first, let me just recall what we all know from our complex analysis course, and that's Jensen formula, which is also called sometimes Poisson-Jensen formula. So it's a formula which helps characterize meromorphic functions in terms of their divisors. So if we start with the disk of radius r centered at the origin, and if we have a non-constant meromorphic function on the closure of this disk, such that it's either Taylor or Laurent series expansion as z tends to 0 has the lead term of the form cf times z to the power m, where m is an integer, so positive or negative, then, of course, there are many ways one can write Jensen's formula from complex analysis. So the way I wrote it in this slide is that it tells us that the integral of the logarithm of the absolute value of f evaluated at the circle, which is the boundary of this disk, plus the sum over all divisors, basically, of function f, of logarithms of absolute value a divided by r, plus the order of f at 0 times log 1 over r equals the logarithm of the absolute value of this lead term in the expansion as z tends to 0. And of course, the order can be either positive or negative, depending on whether the point in the divisor is a 0 or a pole. And of course, we can write the sum over all disk because only finitely many terms are non-zero. Okay, so what would be the so-called modular generalization? So, well, the modular generalization is about characterizing modular forms via their divisors. Okay, so for a meromorphic function on the upper half plane, which is invariant with respect to the modular group, actually PSL2Z is its projection, in which we just identify elements, matrices, let's say matrices A and minus A. So if this is a meromorphic function, invariant with respect to the action of this group, and such that it does not have a pole at the cusp at infinity, and such that its Fourier expansion is normalized, so the constant term at infinity is equal to 1, then Rohrlich Jensen formula actually states that the integral over the fundamental domain of the logarithm of absolute value of our function f, integrated, of course, against the measure mu, which is just the hyperbolic measure, the usual one, dx dy divided by y squared, plus the sum over divisors of function f of the Kronecker limit function is equal to 0. So let me just briefly explain the notation. So the order of f at w is just the classical plus order of 0 or minus the order of pole of function f. The order of w is the order actually of w viewed as the order of the action of PSL2Z on the upper half plane. If we look at points in the fundamental domain, order of every point is 1, unless this point is I or the third root of unity. If it's I, then its order is 2. And if it's the third root of unity, the order is 3, because those points are the torsion points, or we can say they correspond to they correspond to, let's say, elliptic elements of order 2 and 3 inside this group. Okay, the most interesting function here is this function p of w. This function is the logarithm of the absolute value of the usual Dedekind eta function to the power 4 times the imaginary part of the w. And that's something we call the Kronecker limit function associated to parabolic Eisenstein series on PSL2Z. I will discuss this function a little bit more in the sequel, but what I want to say is that this function appears in the constant term of the Laurent series expansion of the classical real analytic non-holomorphic Eisenstein series associated to the modular group. Okay, so how to interpret this modular generalization? Well, we can also interpret it as an inner product of this function with a constant 1, meaning that, and that, of course, this inner product is regularized in the sense that we view it as the limit over the cutoff fundamental domain at the cusp at infinity, where the cut is made at the horizontal line, imaginary part equals capital Y. So we can write the formula as evaluation of this regularized inner product of the logarithm of f with a constant 1, and it equals this right-hand side, which is the sum over the divisor of values of the Kronecker limit function evaluated at zeros or poles of f times a certain constant, depending on their order. Okay, so the logarithm can be replaced by log norm if we assume that instead of being weight 0, meaning being invariant with respect to the group action, if we assume that our function is weight 2k meromorphic modular form, and again, the same condition regarding its Q expansion at infinity. And of course, there are generalizations to other Fuchsian groups, so meaning Fuchsian groups other than the modular group, and they're all derived by Rohrlich. And there are also generalizations, for example, to hyperbolic 3 space. And there is a nice paper by Herrero, Imamoglu, von Pipich, and Toth regarding this topic. Okay. So there is another modular generalization done by Brinkman and Kane recently, I think from 3 years ago. So again, let's keep the modular group setting, but what Brinkman and Kane did is they evaluated a more general inner product. Okay, so what did they evaluate? So we all know that the modular group has a function field of meromorphic functions, which is generated by one element. The generator of this function field is the well-known Haupt module, which arises in many, many applications. And for this particular setup, we will denote by J1 the Haupt module normalized so that the constant coefficient of the Q expansion of this function equals 0. And then by Jn, we will denote the action of the nth Hecke operator to the function J1, to the Haupt module normalized, so that the constant term equals to 0. So let this be Jn, and just let f be the usual weight 2k meromorphic modular form, normalized, so its Fourier expansion at the cusp begins with 1 again. Okay, so the modular generalization by Brinkman and Kay actually amounts to computing regularized inner product of the log norm of f, but no longer against constant, which is 1 or any constant, but against this function Jn, which is J1 acted upon by the Hecke, the nth Hecke operator. So what they did, they evaluated this regularized product in terms of the divisor of f, and again, regularization is needed at the cusp, and again, the integral is interpreted as the limit along the compact part, where f of y is cut off at imaginary part z equals w. And what was proved by Brinkman and Kay is that this regularized inner product equals, again, a very similar sum to the sum obtained by Rohrlich, and that is the sum on the right-hand side, where instead of the parabolic Kronecker limit function, one has a certain form, which in their paper was characterized in terms of certain differential operators. But actually, one can show, and we did in this paper, that actually this Jn of W is just the derivative of the Niebuhr-Poincaré series, which I will also discuss in more detail later. So it's the derivative of the Niebuhr-Poincaré series at s equals 1, minus the sum of divisors function times the same Kronecker limit function P of W. Okay, so now that we see all those generalizations of the Rohrlich formula, it is obvious that the main goal of this talk and of the work that I'm describing is actually to extend the point of view that the Rohrlich-Jensen formula is the evaluation of a particular type of inner product. Okay, so what type of inner product we look at? Well, what we will do also is we will extend this new formula to the setting of arbitrary, not necessarily arithmetic Fuchsian groups of the first kind, but having one cusp, though it is possible to generalize this even further to Fuchsian groups with more cusps. And then what we will do, we will derive some applications and present explicit computations using this extended formula. Okay, so how to revisit this inner product? Well, if you remember, in this inner product, we have two functions. One of them is Jn of z, whose role we will revisit, and another function is the log norm of f, and then we will revisit both functions. Okay, so we recall that Jn is just the action of the nth Hecke operator to J1, And that's up to a constant, the unique holomorphic function, which is PSL2Z invariant, and which has a Q expansion, which begins with a Q to the minus N, and then all the other negative terms in the Q expansion are equal to 0. And then we recall that these properties hold also for the special value at S equal 1 of the Niebuhr-Poincaré series. I will denote the Niebuhr-Poincaré series F minus N gamma of ZS, which are defined for any Fuchsian group gamma of the first kind by this expression, which is of course valid only for the real part S bigger than 1. When S is equal to 1, actually Niebuhr, in his paper, which is in mid-70s, he proved actually that this function has a meromorphic continuation in S to the entire complex plane, and that the function is holomorphic at S equals 1. Moreover, this function, in which gamma is any group, let's say with one cusp, and M is any integer different from 0, this function is an eigenfunction of the hyperbolic Laplacian with the eigenvalue S1 minus S, and it is moreover orthogonal to constant functions. And when gamma is a modular group, then the Niebuhr-Poincaré series at 1 is exactly Jn modulo this constant term 1 over 2 pi square root n plus, and this is also explicitly computable constant, but I just put Cn because it's not really important what it is for the moment. Okay, so instead of Jn, we can actually look at the inner product with the Niebuhr-Poincaré series. Okay, so what about the term, the log norm of f of z? Well, it's a bit more complicated to express this term in a certain way, and it involves findings of another paper that is joined with Jay and Anna von Pipi. And there is also some additional work needed to deduce this proposition that I write here. So for any cofinite Fuchsian group with one cusp which is, of course, which one can take to be at infinity without loss of generality, and such that such that the scaling matrix is identity as well. And let F be this weight 2k meromorphic form, gamma invariant, Q expansion at infinity normalized, so the constant term is equal to 1. So this is the same meromorphic modular form as before, but the result says that the log norm actually is minus 2k plus the sum over the divisors of F of, I will call these forms prime forms. So it is the sum of prime forms, where the prime form is basically the limit as S tends to 1 of the hyperbolic Green's function associated to gamma plus the parabolic Eisenstein series associated to gamma. And there are two equivalent ways to write this formula. The second one follows from the Riemann-Roch type theorem. Okay, so I will not prove this, but the key idea in the proof is the fact that this function, I will discuss shortly, has the logarithmic singularity as z approaches w, so does the function on the left-hand side. And the order of the singularity will match accordingly. Okay, so just let me now explain the notation, what this part is. This is the parabolic Eisenstein series, and what this function is. Okay, so the parabolic Eisenstein series is the classical one. So it's the sum over the cosets of the action. So the sum over the cosets of the action of the stabilizer at infinity of imaginary part gamma z to the power s, of course, real part s bigger than 1. Of course, the series is well-known, well-studied, real analytic series, and there is a well-known Kronecker limit formula, which states that as s tends to 1, the parabolic Eisenstein series has a simple pole with a residue 1 over volume, and the next other term, meaning the constant term, as s tends to 1, is a certain real constant beta minus 1 over the volume times the logarithm of a certain holomorphic form. This is the result of Goldstein, also from mid-70s. And this function, eta infinity, is a holomorphic form which can be viewed as a generalization of the classical eta function. And then this function, logarithm of eta infinity to the power 4 times imaginary part of z, is again called the Kronecker limit function. Okay, so the Green's function is also called the resolvent kernel. That's the function given in terms as a sum over the whole group of a certain point pair invariant, which looks kind of not so nice, but it possesses some very nice properties. So this is the point pair invariant. And the Green's function has some very nice properties, which are the following. So the Green's function is vanishing at the cusp. It has a logarithmic singularity when viewed inside the fundamental domain. So the logarithmic singularity is of the type order of w divided by 2 pi times the logarithm of absolute value z minus w. And of course, I have to say that there exist different normalizations for this function gs. It can be also given in terms of the Legendre function qs minus 1. It can also be given in terms of, in different ways as a hypergeometric function. So this seed ks can be different in different papers, but all generalization, all definitions that I've seen so far, they differ by a constant factor, which is plus minus 2 pi, plus minus 2, plus minus 4 pi, and so on. And what is really important for this talk is that both GS, the resolvent kernel, and the parabolic Eisenstein series are also eigenfunctions of the hyperbolic Laplacian with the same eigenvalue s times 1 minus s. Okay. So then what about the limit as s tends to 1 of this sum? Well, this limit is also a very nice function. It's holomorphic, actually, as s tends to 1. Why? Because the Green's function, as proved by Niebuhr, has the following Fourier expansion. It's given on the slide. And once the parabolic Eisenstein series is added, then basically this function is holomorphic in S with logarithmic singularity as z tends to w. So this is the term which is our prime form. Okay, so what is the inner product for us to consider? So if you go back, what we want to generalize, we want to generalize this inner product. So instead of Jn, we will take the Niebuhr-Poincare series, and instead of the log norm, we will take one prime form, which is the limit as s tends to 1 of the sum of the Green's function and the parabolic Eisenstein series. Okay, so what is our inner product to consider? Well, it's just this inner product. Lieber-Poincare series, and the prime form, of course, prime form bar, because by definition of the inner product, we will, of course, regularize it only at the cusp at infinity. Why? Because this singularity as z tends to w is logarithmic, and the logarithmic singularity is integrable, so there is need only to regularize the inner product at the cusp, and the regularization is again the limit as y tends to infinity of the integral over the cutoff domain of the product of two functions integrated, of course, against the hyperbolic area element d mu hyperbolic of z. Okay, so what is the key observation that will help us evaluate this inner product? Well, I've already told this, and the key observation is that all terms in the product are eigenfunctions of the Laplacian with the same eigenvalue. So actually the inner product for people who work a lot with trace formulas can be computed in a manner which is similar to that which yields the Maas-Zellberg formula. Okay, so what is the key identity to start with? Well, this first two lines actually discover a small trick. So we know that those functions are eigenfunctions of the Laplacian with the eigenvalue s times 1 minus s. So how to use that? Well, if one looks at the second line on this slide, which consists of 4 big ugly lines, one can see that actually if we take minus s times 1 minus s in front of the integral and differentiate with respect to s, and then plug in s equals 1, that actually this is the same integral we had before. And of course, given that s times 1 minus s is the eigenvalue of our Green's function and f minus n, then we can write this as actually, so this term here, the second line equals, the second line equals the fourth line, and the third line is actually 0. Why? Because f minus n at z1 is the eigenfunction of the hyperbolic Laplacian with eigenvalue 0. So actually this third line is 0, but I put it here because this is what amounts to, this is the formula to which one can apply Green's formula. So the integral of delta f times g minus f times delta g can be written in terms of exterior derivatives along the boundary of f. So after application of Green's formula, of course in hyperbolic geometry, to this difference, one ends up with the regularized product being written as, of course, the limit of the derivative with respect to s at s equals 1 of the exterior derivatives of the integral along the boundary of the exterior derivatives. But basically, all the exterior derivatives cancel out because the fundamental domain has boundaries that can that match and have the opposite direction of the normal. So the only derivative that remains uncancelled is the derivative along the cut-off part of the fundamental domain, which is this integral from 0 to 1 dx, and the derivative is, of course, with respect to y, and evaluated at z equals x plus iy, where y, capital Y, is just the cut-off parameter. Okay, so this looks very nice. Why? because this is now a good place to use Fourier expansion and orthogonality of exponentials. So now the heavy computation starts. I will, of course, skip all that. So we have, the Fourier expansions of all those functions are well known. They are kind of not so nice. They're big. They involve different types of special functions, I Bessels, J Bessels, and K Bessels, and so on. But after a long computation, kind of miraculously, everything somehow cancels out. And the main theorem of this work shows that actually this regularized inner product equals just minus the derivative with respect to S of the Niebuhr-Poincaré series evaluated at 1. So this must be true. I mean, this is of course proved, but if you see how neat this result is, somehow by the principle of beauty of mathematics, it has to be true. Okay, and then we can continue. So instead of this prime form, we can, of course, use the expression for the log norm of f to generalize further the Rohrlich-Jensen theorem. So we have that the regularized inner product of f minus n with the log norm of f is actually a very similar looking formula to the previous one, where instead of the Kronecker limit function, now we have this derivative of f minus n at s equals 1. And again, assumptions on f are the same throughout this whole talk. Of course, one can generalize further because it is well-known result of Niebuhr that any G invariant, any function G, which is gamma invariant and analytic, and has a pole at infinity, for every such function, we can express it as a linear combination of Niebuhr-Poincaré series, where this an is a constant depending on the function j, and c of g, on the function g, and the c of g is also depending upon g. So then we have the inner product of the two forms. One has a pole at infinity, another one can have poles inside the domain, but not at infinity. And the inner product is a bit more involved formula, but still, again, expressed in terms of the divisor of function f. Okay, so in this paper, we did go further. So we also looked at the generating series for this interesting function that popped out as a regularized inner product. And the generating series for this function, where qz is e to the 2 pi I z. So the generating series is a function of two variables, z and w. So when viewed as a function in the z variable, this generating series turned out to be the holomorphic part of the weight 2 biharmonic mass form, this gw of z, which is basically the derivative of our prime form at 1, and then which is actually the raising operator up to the factor of 2, I delta delta z, of the derivative at s equals 1 of this prime form. Where by biharmonic, I mean that, of course, weight 2 satisfies weight 2 modularity in z and is annihilated by the weighted Laplacian delta 2, but squared. That's why b. And delta 2 is just psi 0 composed with psi 2, where psi is the classical psi operator in the theory of modular forms. Okay, so I don't know how much time do I have, maybe 10 or maybe 7, 8 more minutes.
No, you still have time. You still have almost, well, 20 minutes actually.
Oh, 20 minutes.
Mhm.
Okay, great. I was not sure how long should I talk. So, okay, great. So I can go then through the applications. Happy to do so. So what are the applications I want to present? Well, I would like to discuss a little bit what happens if our group gamma is not a modular group, but when the group gamma is a nice Fuchsian group with one cusp, which is commensurable with the modular group. But it is not the subgroup of the modular group. Why? Because we have this square root here. So that is a group which is obtained by adding all Aitken-Lerner involutions to the usual congruence subgroup. So we will look at the square free level n, which is a product of r different primes. So the case n equals 1 is just the modular group. So, and the Aitken-Lerner group can be defined by gamma naught n, by the group generated by gamma naught n and all Aitken-Lerner involutions, or in this way very explicitly. So it is a group of the matrices with the stated properties. So this is a nice group which has one cusp. And then we will denote by yn plus the corresponding Riemannian surface. And this bar here denotes actually the projection of this group, which is a subgroup of SL2R onto PSL2R, meaning I will just identify elements plus minus the matrix inside the group. So for such groups, we can make all the terms in the Rohrlich-Jensen formula very explicit. So the Kronecker limit formula for the parabolic Eisenstein series associated to this group of level n is of this type, where we have very explicit forms for the constant Bn, which depends only upon the number n, and of course its prime factors. And there is a cute little zeta primed at -1. This is the value of the Riemann zeta at -1. And this Kronecker limit function, Pn of z, is also, one can also, it's not really easy, but it's possible to explicitly compute this function. We did it in the joint paper with Jay and Holger then. So this Pn of z is the log of the 2 to the rth root of the product of the classical Dedekind eta function over the divisors of n. And then, of course, when the level is 1, then we just retain results by Brinkman and Kane, meaning that when J is just the action of the Hecke group on J1, we get the result from Brinkman and Kane. And I will just, as a side comment, add that actually those derivatives at s equals 1 are not a function that appears in this work for the first time. So in the case of the modular group, in a paper by Jeong, Kang, and Kim, it's proved that actually this Hn star, which is a psi0 action on this derivative at s equals 1, it's a harmonic weak mass form of weight 2. And moreover, this for positive n, it equals 4 pi times Hn of w, where this set, Hm of w, for where m now runs over all z, is the basis a certain basis. I did not write it explicitly here for negative m's, for the space of weight 2 harmonic weak mass forms, and this basis was deduced by Duke, Imamoglu, and Toth. So I just wanted to mention that in the modular group case, this function already appears and is related to the basis for the space of weight 2 harmonic weak mass forms. Okay, so what about other levels? Well, this depends upon the genus. Why depends upon the genus? Well, when the genus is 0, then it is well known that the space of meromorphic functions on the group or on the fundamental domain or on the Riemannian surface, depending on how we want to view this space, the space is generated by one function, which is the Haupt module. And the Haupt module is determined by the property that the Q expansion at infinity begins with 1 over Q. And then we have lower order terms. And regarding the Atkin-Lerner groups, there are exactly 44 levels for which the space has genus, this corresponding space has genus 0. And for each such genus, there is the Haupt module for this genus 0 is computed. I think it goes back to the work of Conway and Norton because this is all related to the monstrous moonshine conjectures. So the Haupt module for these genus 0 Atkin-Lerner groups are just Jn pluses. And of course, the action of the mth Hecke operator to the Haupt module again has the same type of expansion. And then, by just using the properties of the Niebuhr-Poincare series, this Jn, the Tm action on Jn plus can be expressed explicitly in terms of the Niebuhr-Poincare series, and this is just the constant term in the approximation, and the constant term is just 24 times the sum of divisors times a certain function which depends only upon primes dividing the level n. This is all for genus 0. So what is the prime form in this setting? Well, the prime form is the analog of the delta function on the modular group. In which case the analog? Well, the analog in the sense, in which sense it's the analog? In the sense that delta n is a minimal weight holomorphic form for this group, which vanishes only at the cusp. And the minimal weight is known from the work that is joined with J and Holger. And this weight is 2 to the r minus 1 times ln, where ln is just this number expressed in terms of the level n. And the prime form is just this delta times the difference of the Haupt modules to the power nu n, where nu n is the order of vanishing of delta n. And the prime form is nice. It is just the product of eta functions over the divisors to the power ln times the difference of the Haupt modules to the power nu n, where nu n is the order of vanishing of delta n. Okay, so actually, in this case, we have a very explicit expression for the regularized inner product of the action of Hecke on Jn plus and the prime form, and it is given on this slide. I just want to say that it's explicit in terms of Dedekind eta function, in terms of the derivative of the Niebuhr-Poincare series at s equals 1, and all other terms depend singly on the level m. Okay, and I will give just the last one example, which is a genus 1 example. So the smallest level for which genus is 1 is the level 37. So for this level, again, everything can be even more explicitly computed. I just wanted to show you that for this level, of course, how the genus 1 differs from genus 0, and of course, all other genuses that are positive differ from genus 0 in the sense that the function field of neuromorphic functions is now generated by 2 functions, no longer 1 function. And in the case when the genus is 37, function field generators are explicitly known, and they're explicitly known for all genus 1 and genus 2 and genus 3 levels. And in this genus 1 level case, I just wrote down the Q expansion with a few terms for the functional field generators, and they satisfy this cubic relation of this type. And of course, all the constants that I mentioned before can now explicitly computed. For example, this constant beta 37, which is a constant term, one part of the constant term in the expansion, in the Laurent series expansion of the Eisenstein series, is presented here. The hyperbolic volume is 19 pi over 3, and so on. So the prime form in this case is weight 24 holomorphic form of this type. So it's delta 37 squared times the difference of x's to the power 19. Of course, it is possible also to look at y's, but then the computation is slightly different. And we have inner products of x with the log of f37w and of y with the log of 37w. And one can see that everything is explicit in terms of, again, Niebuhr-Poincaré series derivative at 1. And all other terms involve just simple Dedekind eta function and just the numbers. And of course, our favorite constant zeta primed at -1. Okay, so thank you for attention.
Thanks a lot. Let me cut the recording before.
Okay, I will
the questions.
now somehow stop recording, stop presenting.